All right, guys, we should all be pretty much back on the same page by now. So yeah, some simple gas law stuff there and a unit conversion to do. So basically out of last Friday's lecture for us to look at. So we're going to go ahead and continue with that. Obviously no video last night to worry about. If you did watch one, hey, you're ahead of the game. So good for you. Do remember though, we do have a video for Wednesday, and that one's going to be the one about the applications of the ideal gas equation. I forget what the number is, but that's the one you want to look at. Okay, so we'll actually hopefully get to the ideal gas equation today and just talk a little bit about it and do a simple example. And then the video is going to cover some other applications of it. But what I want to do today is I want to finish up with some of the simple gas laws. Now, if you remember from Friday, what we did was we looked at 3 simple gas laws, all involving pressure, okay? So what we were doing was we were looking at how pressure depends upon things like volume, temperature, and number of moles, right? So what we can do is we can also come up with some equivalent volume relationships. So I want to look at those volume relationships today. So those basically just turn out to be subsets of the other ones that we talked about. All right, so our first one is going to be the volume variation of Charles's law. Okay, so we can recast Charles's law. Now remember what Charles's law said last time, back when we were talking about it on Friday. That was the one that related pressure and temperature, right? At constant volume and number of moles. Well, I can recast that now. It's the temperature one. Okay, but now I can recast it in terms of volume. So we would do it the very same way as we did it before. So I'm going to start out with the ideal gas equation, PV equals nRT. And now rather than solving for pressure, I'm going to solve it for volume because I want to put these in terms of volume. So if I do that, volume is going to equal to N times R times T divided by pressure. All right, since we know that Charles's law is the temperature law, all right, what things are we going to hold constant? Well, we're going to hold N constant, R is already a constant. We're going to hold pressure constant, okay? So now what I can do is I can bring another constant into this. I think we used A, B, and C last time as our constant, so that would leave us with D. So I could rewrite this as volume is equal to a constant D times temperature, okay? Another way of stating that is that volume and temperature are proportionally related to each other at constant N and constant pressure. So we'll just show that as well. So we remember what's remaining constant here. All right, so what does that mean? Well, at constant N and P, if I increase the temperature, what's going to happen to the gas? Well, it's going to expand. So in other words, the volume is going to get bigger. And that makes sense if we think about it. Like we talk about our balloon. Okay, if I were to heat up the atoms or molecules inside of the balloon, they're going to move faster. And at a constant external pressure, what's going to happen is the balloon is going to expand in response to that. Okay, so that's why volume and temperature are going to be proportional. All right, so now how did we do it from there? Well, I wanted to get an initial final relationship so I can compare a set of initial conditions to final conditions. So I solved for the constant. So D is equal to V divided by T. And what that meant is that for any set of initial and final parameters that I've got in terms of V and T, they have to ratio out to D. So in other words, I can say that V initial, T initial has to equal to V final over T final. Okay, so that's the useful form in terms of initial and final conditions for the volume relationship of Charles's law. Okay. So in other words, I can just recast Charles's law, the temperature law, in terms of volume instead of pressure. So that's another useful variation of it. One other thing I should mention, I hope I mentioned it last time when we were talking about Charles's law with regard to pressure, but it applies both places. And that is, I'll put an asterisk here to remember it. We always want to cast temperature in terms of Kelvin. The reason why we do that is because if we use Celsius and the temperature gets too low, we get into negative values. when we start looking at these proportional relationships, negative values don't really make any sense. So that's why we want to use absolute temperature units here. Now, in terms of like volumes, it can be any volume unit. It could be a milliliter, a cubic meter, a liter, whatever. But the temperatures need to be in terms of kelvins. And that's true for the pressure relationship of Charles's law as well. All right, then the other one we can cast in terms of a volume relationship is going to be Avogadro's law. That's the mole one. That was the one on the quiz, right? All right, so for Avogadro's law, we can do the very same thing. We can say that PV equals to N times R times T. I'm going to cast it in terms of volume now. So volume is equal to N times R times T divided by P again. And now we want to see what's held constant. Now, since Avogadro's law is the mole law, okay, that means we're going to keep R constant, T is constant, and P is constant. And we're going to let N, which is the number of moles, vary with volume. So what we see here is, what's our next thing we're going to use? We'll use E for our constant. Okay, so we can say that V is equal to proportionality constant E times N. Okay, so that tells me, of course, that as the number of moles of gas inside of a balloon increases at constant pressure and temperature, well, the volume ought to increase as well, because you're putting more moles of gas in there. So that makes sense. All right, so now and then we'll just make sure we know that it's at constant, what do we say, T and P. Okay, so now if I solve this thing for E, E is going to equal to V divided by N. So now I can set it up in terms of an initial final relationship. V initial over N initial is equal to V final over N final. So there's our useful volume number of moles relationship. Okay, so they work just like the ones we had before. Now, why don't I do one for a volume related Boyle's law? Well, that's V and P, because I end up coming up with exactly the same relationship that I did before between V and P. So there's no point in doing that. We'll get exactly the same answer as we do for the pressure case. Okay, so those are all of the simple gas laws that we have to worry about. Now, there's one more that's worth talking about here that it does come into play from time to time. And as a matter of fact, I think it comes into play in the lab you guys do. And that's called the combined gas law. Now, what the combined gas law does is it's going to relate pressure, volume, and temperature at a constant number of moles. Okay, so again, we can derive it exactly the same way as we did before using the ideal gas equation, PV equals nRT. Okay, now I can put it in terms of, doesn't matter, pressure, whatever the case, we'll put it in terms of, well, let's just leave it like here. What do we need to put constant here? Well, we need the constant to be N, the number of moles, and R. Okay, everything else is going to vary. Okay, so now we could actually rewrite this as PV is equal to a new constant F times T. So now if I solve for F, my constant, that's going to equal to PV over T. So now we know how to get to our initial final relationships. If that's a P initial, V initial, T initial, that's going to have to ratio out to P final, V final over T final. So that's relating three of the variables at the same time instead of just two. So sometimes that combined gas law is useful to use. Matter of fact, we're going to do a example problem involving it here in just a moment. Okay, so outside of the ideal gas equation, these are all of the various gas laws that are going to be useful to you. So again, how do I know when to use them? Well, you kind of have to look at the problem and see what the problem is asking for. Is it an initial final kind of problem? And if it is, this is the set of gas laws we probably use. And then we have to see which variables are changing and which ones are remaining constant. Okay, I've been talking a lot. Do you guys have any questions at this point? Everybody good? All right. So at this point, let's take a look at an example problem here. Now, I'm not going to write the whole thing out here because it's essentially going to be a initial final kind of problem. And it's going to involve a weather balloon. So you guys know about weather balloons, right? So they basically attach measuring devices to this balloon. They usually put helium in it, I think. And then they set it off at ground level and it goes up into the atmosphere and the measurements are made up there. Okay. Now, when you actually work with a weather balloon, you have to actually generate some room for expansion there. Okay. Because what ends up happening is we're going to fill the balloon with gas at ground level or sea level or wherever we set it off from. But then as the balloon rises, okay, the temperature goes down. But the other thing that happens is the atmospheric pressure also goes down. So what ends up happening is, given a set number of moles, the balloon is going to expand. So you have to actually make room for the balloon to expand as it rises, or otherwise it'll explode on you and you'll lose all your gear, not be able to make the measurement. So here's some data involving a weather balloon. So we're going to say on the ground, this is going to be our initial set of conditions. Here's what we have. All right, my initial pressure is going to be 1 atmosphere. Okay, so that's kind of like we know we're setting this off right at sea level because we always know that sea level is 1 atmosphere of pressure. The initial volume of the balloon before it rises up is 2.00 times 10 to the 3rd meters cubed. Okay, and then the T initial, that's going to be the temperature at the ground, is 27 degrees Celsius. But we know what we have to do. We have to turn that into a Kelvin temperature. I know how to do that. I'm going to add 273 to it, and that's going to give me 300 Kelvin. And we'll keep all 3 of those sig figs there. Now, once the balloon rises up, it gets up into the air. So we'll say at altitude, after it rises up into the atmosphere, that's going to be my final set of conditions. And here's what we know. We know the P final, that's going to equal to 0.340 atmospheres. Now notice that went down at ground level or sea level, we're at 1 atmosphere, but up at altitude, we're at roughly about 1/3 of that. So that tells me that the atmospheric pressure is decreasing with altitude, and we know that happens. Like I said, we expect the balloon to expand because of that lower pressure, and it does. And that new volume is 5.00 times 10 to the 3rd meters cubed. Okay, so the balloon got bigger. So that's actually a good example of Boyle's law, pressure volume relationship. So notice that as the pressure got smaller, the balloon got bigger. That's that inverse pressure volume relationship we talked about on Friday. Okay, and then what we want to know is the T final. Okay, so there's going to be some temperature that at that pressure and volume is going to give me that volume of the balloon. Okay, so we want to find out what that temperature is. So again, we kind of have to look at what variables are involved. We know it's an initial final kind of problem, so that tells me I'm going to use one of the simple gas laws up to and including the combined gas law. Okay, so what have we got changing? We got pressure, volume, and temperature changing. What's remaining constant? The number of moles of gas inside the balloon. Okay, so that doesn't change. We're going to assume that all the gas we put in the balloon stays in the balloon. So that's constant. So what that means is I want to use the combined gas law. So let's remind ourselves of what the combined gas law says. It says P initial, V initial over T initial is equal to P final, V final over T final. Okay, so now we got to do a little algebra, right? So ultimately what we want to do is solve for T final. So there's a little bit of rearranging involved here, which I did. Make sure you guys can do this on your own. So T final equals to T initial times P final times V final divided by P initial and V initial. Yep, got that right. So again, make sure you guys can rearrange the equation to get to that. All right, so now we're going to plug our values in. So T initial was what? 1 atmosphere. Oh, sorry, I'm talking about temperature here. That was 300 Kelvin. I'm getting ahead of myself. P final, oh, that was the final one. So that's going to be what, 0.340 atmospheres. I'm going to put my units in here to make sure that they all cancel out. That'll tell me I probably did my algebra right. V final, that's the final volume. That's 5.00 times 10 to the third meters cubed. Okay. I want to divide that by P initial. That was the 1 atmosphere, right? And my V initial, and that was my initial volume. That's 2.00 times 10 to the third. And that's meters cubed. Okay, so let's just check the units. I should get temperature units back out, so hopefully we do. Looks like atmospheres will cancel top and bottom. Looks like cubic meters are going to cancel top and bottom. That's going to leave me with Kelvin, so I think I did my math right here. And I know for sure because we expect the temperature to be lower at the higher altitude, right? So if it isn't lower, we know we did something wrong. All right, so when I grind all this out to sig figs, my T final turns out to be 255 Kelvin. Okay, and if I want to, I can relate that back to Celsius. Now I can compare it to the 300 Kelvin that I actually had for T initial, and sure enough, it is lower. But if I wanted to go ahead and convert it back into Celsius, I would just subtract 273, and I would get minus 18 degrees C. Okay, so in fact, it is colder at the higher altitude, and that's exactly what we would expect. So that tells me I probably set the problem up correctly. All right, guys, any questions about that?
I have a question.
Sure, go right ahead.
So just looking over the problem again in order to make sure I understand. So how would you differentiate this one from a Charles law? Because I noticed that they have the same constants.
Okay. Yeah, so it's again going back and looking at what's actually changing in the problem, right? So if I go back to Charles's law, that's either your pressure temperature relationship or your volume temperature relationship, right? And both of those are in here, right? I've got a pressure relationship and a temperature relationship. I've got a volume initial and a T initial, and I've got the final ones as well. What tips me off is that both pressure and volume are changing with temperature, okay? So if I had, for example, just pressure and just temperature changing at, say, a constant volume, then I would use the pressure variation of Charles's law. Alternatively, if I had just temperature and just volume changing, and I was at constant pressure, then I could use that volume relationship of Charles's law that we just did. But what's tipping me off here is that pressure, volume, and temperature are all changing at the same time. Okay, so that tells me I have to treat each one of those as a variable. So that leads me to the combined gas law. Does that make sense?
Yes, thank you.
No problem. Glad to do it. Any others, guys? All right. So the last thing I want to talk a little bit about here is I want to sort of revisit the ideal gas equation. We're familiar with it because all of these simple gas laws that we've looked at so far derive from. Okay, so that's always been our starting point. But it's also probably the most useful gas law or gas equation that we have. We're going to use it all the time. So it's worth going back and kind of reintroducing it and then maybe looking at just a simple problem that we might use with it. Okay, so the ideal gas equation. We know what it says. It says PV is equal to N times R times T. Okay, now the important thing here is R. That's that gas constant we introduced. So we'll reintroduce it. Now, when we use the ideal gas equation, we don't have as much latitude with units as we did in the simple gas laws. Really about the only one we really had to worry about is that temperature always has to be in Kelvin. But otherwise, any pressure unit will do, any volume unit will do. Okay, you get the idea. Moles are moles, so that can't change in terms of its units. But what the gas constant is equal to is 0.08206. And watch the units here. It's liters times atmospheres per mole times Kelvin. And that makes sense because if you solve this thing for R, what do you get? R is equal to PV over NT, right? So if you put those units in, okay, volume should be in liters, pressure would be in atmospheres, N would be in terms of number of moles, and T is in terms of kelvins. Okay, so we're pretty much nailing down what those units have to be when we use the ideal gas equation. So for example, if you have a volume in milliliters or cubic meters or something like that, you got to turn it into liters. The only other thing I might mention here, this is always the way I've learned it. Chem 101 for some reason likes to use bars instead of atmospheres. They're almost the same thing. So actually, when you start playing around with Chem 101, you'll see the gas constant will vary. I think it's like 0.08306 or something like that. And it'll be in terms of liters, bars per mole Kelvin. Okay, no problem. It's just using a slightly different temperature unit that changes the constant a little bit. And Chem 101 likes bars instead of atmospheres, and that's fine. It just changes the constant a bit. Okay, but it works exactly the same way. So don't get scared when you see that. It's the very same thing. A bar is actually almost equal to an atmosphere. In most cases, we almost use them interchangeably. All right, so let's take a look at a simple example problem. This is, about as simple as they get. So we could say, we'll just write it out. What is the volume in milliliters occupied by 89.2 grams of gaseous CO2 at 37 degrees Celsius and an external pressure of 737 millimeters of mercury. Okay, so the reason I know I can use the ideal gas law here, and this is one of the questions students ask me all the time, when do I know when to use which gas equation? In this one, I know I'm going to use the ideal gas law, partly because of the information that's given, but also because there's no initial final stuff going on here. I'm just setting, okay, an N through the grams of CO2. I'm setting a temperature and I'm setting a pressure. Okay, so there's no initial final. There's nothing changing here. I just want to determine the volume of that ensemble of gas particles. That's all I'm after. Okay, so I'm going to use PV equals nRT for this. But before I do that, I got to get everything into the right units. So the gas constant's going to lead me there. Okay, so I need liters. Well, that's what I'm going to be solving for, but I can then convert that to milliliters. All right, I've got 89.2 grams of carbon dioxide. Okay. Oh, but I need to get it in terms of moles, don't I? But that's okay. Once I've got grams, I know how to get to moles of anything. We're good at that. Okay, so I know that 1 mole of CO2 is equal to about 44.02 grams of CO2, and that comes from the molar mass from the periodic table. So grams cancel with grams, and I end up with, let's see, 2.02635, more sig figs than I need, moles of CO2. So let's see, we're going to be good to 3 sig figs, so I'll underline that to remind myself. Okay, we got a temperature of 37 degrees Celsius. Oh, but I want to get that to Kelvin, so we know how to do that. We're going to add 273. If you want to put the 0.15 on it, that's fine. I usually just leave it at 273. And when you get there, you end up with 310 Kelvin. And again, it looks like we're good to 3 sig figs there. I'll go ahead and underline that just to remind us. Then we got the pressure. So I got 737 millimeters of mercury here. And I need to get that over into atmospheres. Okay, so we know the conversion for that. I know that 1 atmosphere is equal to 760 millimeters of mercury. Okay, And if you wanted to do this in terms of bars, you could look up the conversion between millimeters of mercury and bars. All right, and what I end up getting here is 0.970 atmospheres. Okay, and that looks like it's also going to be good to 3 sig figs. So I think we got everything we need now. So we need volume, right? That's what I'm asked for. So I'm just going to solve the ideal gas equation for volume. So volume is going to equal to N times R times T divided by P. And now I'm just going to stick everything in there. Okay, so I know that my V is equal to my number of moles. That was what, 2.02. I'm going to keep all the digits, so I don't get any rounding error. Moles, so we'll just put moles in there. Okay, and I need R, that's 0.08206 liter atmospheres per mole Kelvin. And then this last thing I need is temperature, and that's 310 Kelvin. Okay, now I got to divide all that by the pressure, don't I? So I'm going to put a big line there, and what was my pressure? 0.970 atmospheres. And again, the hardest thing about this, which really isn't hard, is trying to make sure that all of the units align, right? So make sure you're paying attention to the units and getting them into the correct format there. So let's make sure it all works. I should get volume units out of this, which would be liters. In the top, canceling with an atmosphere in the bottom down there. So it looks like I'm left with liters. That's what I want. So now my volume, when I work it out, turns out to be to 3 sig figs, right? That's what we need. 53.1 liters, but they wanted milliliters, didn't they? But that's easy. So we know that 1 liter is what, 1,000 milliliters. That's an easy one to do and remember. And I end up to sig figs 5.31 times 10 to the 4th milliliters. There you go. Okay, so a pretty straightforward example there. All right, any questions about that? Because I kind of want to get back into Chem 101 here and have us practice a little bit with some of this. Got to admit, this is easier than redox, right? All right, so let's pop back over. Yeah, I hear you. I'm with you. All right, so let's go back over to in class here. And we're back into chapter 9. We'll do the first one. So that's gases and pressure. So yeah, looks like we're going to time out about perfectly here. Okay, looks like it's running. So let's just kind of look at it here and see what we got. And some of these are really easy, guys. It's really just kind of reviewing some really basic stuff that we've already talked about here. Should be able to zip right through it. You remember those torrs, guys. Remember, a torr is the same thing as a millimeter of mercury. All right, guys, looks like it timed out. Anybody got any questions or concerns about any of those? All right, looks like everybody's okay. So that pretty much does it for today. Just as a quick reminder, make sure you're watching the next video, which is applications of the ideal gas equation, and be ready for another 5 for 5 on Wednesday. All right, folks, have a great day. Enjoy the outdoors. It's beautiful out there. And I'll see you guys on Wednesday.